people are still coming in, but anyway, let's get started. So welcome to the Apache Sedona Community Office Hour for the month of July. My name is Jia. I'm the PMC chair of Apache Sedona. And today, the agenda is as follows. So first of all, the big one, SedonaDB 0.4 release. So it was released on June 19th. I will walk through everything that is new, and then a sneak peek of the next Apache Sedona Spark release 191. And at the end, we have a special guest, James Willis, an Apache Sedona committer, and he will give us a short presentation about his work on the recent SedonaDB n-dimensional array rasters. First of all, for people who are new here, a quick word about Apache Sedona. So Sedona is the most popular open source engine for processing big geospatial data. So it started as a research project, but now it is an Apache Software Foundation top-level project. And you can find its website and GitHub repo here. And we also have social media account on X and on LinkedIn. So be sure to follow us and get the latest news about the project. And the Apache Sedona ecosystem keeps growing. So we recently passed the 70 million total downloads. And now we are also getting more than 2 million downloads every month. And more than 170 people have contributed code to Apache Sedona. And thank you to everyone who is here today. And as you see all the logos there, so Sedona is being used in many companies in production, right? From very different industry sectors. And Sedona can handle geospatial data at any scale. For very large data on cluster, we can use Sedona Spark and Sedona Flink, as well as Sedona Snow. For small medium data on one machine, we can use SedonaDB, which is a single node Rust engine. We recently also have another sub-project called the Spatial Bench to actually compare the engine performance in a fair way. Here is the system architecture about the Sedona Spark in particular, which is a distributed mode. The distributed side of Sedona has 3 layers. So the top layer is the spatial query processing layer. So it has a number of APIs that connects to developer tools, including Scala Java API, Spatial SQL, Python, and R. You can connect them to Apache Zeppelin, Tableau, Jupyter, and RStudio, as well as GeoPandas. And in the spatial query processing layer, it has different query algorithm, and we also have a query optimizer that can automatically choose the best query algorithm given a spatial query, and also some characteristics of the input dataset. We have different query operators, including k-nearest neighbor join, k-nearest neighbor query, spatial join as well, and lots of raster functions. So the second layer is the distributed spatial dataset layer. It has spatial partitioning, spatial indexing, serialization as well. And at the bottom, Sedona can run on top of a number of different distributed engines, including Apache Spark for batch processing, Apache Flink for stream data processing, and Snowflake also for batch data processing. And by far, our support on Apache Spark is the most comprehensive one. And here is the architecture of SedonaDB, which is the single node engine we released last year. It is purely written in Rust. And SedonaDB runs on your laptop or one server. It is built in Rust on top of Apache Data Fusion and Apache Arrow. The data is columnar in memory, so the queries are very fast. We also have a spatial query optimizer spatial join algorithm. And as of the recent 0.4 release, we also started to add some basic raster and ND array functions, and I'll show them very soon. So if you want to try Sedona today, so here are the easy paths. First, Sedona Spark. The easiest way to use it, I'll give it a try, is just pull the Docker image and run. And you will get Jupyter and Spark UI ready to use through a Docker image. And for SedonaDB, so all you need to do is one pip install and a few lines of Python. Then you can start to use the SedonaDB function. And the release cadence. We ship a release almost every 3 months. This keeps the project moving and easy to follow. You can see the recent versions for Sedona Spark, SedonaDB, and Spatial Bench. Uh, the last release of Sedona was April, right? So we're gonna have another release for Apache Sedona Spark very soon. The 191 release is supposed to be out this month in July. And for SedonaDB, we recently made a new release, 0.4 release on June 19th. And Spatial Bench, we made a new release earlier this year. Since then, we don't have lots of updates in the Spatial Bench project, so we haven't made a new release yet. Now, let's talk about SedonaDB. SedonaDB 0.4 was released, like I mentioned, on June 19th, and many new features are included in SedonaDB 0.4, right? Some context first. So SedonaDB is still a young project. So the first release was less than a year ago. And so since then, each release has big new features. So the 0.1 release has some basic functions. 0.2 brought k-nearest neighbor join and Parquet 1.1 write. And the 0.3 brought larger the memory spatial join, item level CS, and point cloud data support. Now, the 0.4 release is out, and this is our biggest release so far. So we resolved 187 issues in this release, and they are actually from more than 15 contributors. And we now have 176 functions in total, and we test them against Postgres BigQuery for correctness. And the highlights are on the slide. And in this release, we also have a new Python DataFrame API and an R interface and a full rewrite of the geography data type, GPU accelerated spatial joins, and the GeoParquet 2.0 write support, and n-dimension array with star. And I haven't seen James yet in the meeting, but James will talk about the ND array ZAR support, which was contributed by him. So first of all, packaging. SedonaDB is now on conda-forge. Many people in the geospatial and scientific Python world live in conda. So until now, they had to mix pip into their conda environment. Not anymore. So one conda install command and you are ready. Of course, pip still works too. And big thanks to the contributor who drove this. And second, the new Python DataFrame API. So before 0.4 release, the main way to use NDB from Python was SQL string. SQL is great, but many Python users prefer to build queries with code. So we added a DataFrame API. It is inspired by the tools that you already know, Avis, DuckDB, PySpark, DataFusion, Pandas, and GeoPandas. And look at the example here. You read two files and you join them with st-intersect, and then you can do filter, select, sort, and limit, and all chainable and all lazy. And there is also a geo accessor on the geometry column, so you can chain geometry operations as well. So you can do, for example, you first do a centroid on the data, and then you can do a buffer on the function. And also every function has inline documentation, so autocomplete works in your IDE. Third, uh, R users also get same love. So there are two new package, SDBLYR and Sedona FNS. And the first one gives you the dplyr style verbs on top of SedonaDB. And this code should work very familiar. And the filter select arrange head and a spatial join with SD join intersects. And the second one expose the full catalog of Sedona function to R. So both are available from the Apache R universe. So the R spatial community can use SedonaDB without leaving their workflow. And another one, the geography support, which is rewritten on S2 geography this time. And some context first. Most spatial engines work on a flat 2D plane, and that works fine for one city or one country. But the Earth is round. So when our data covers the whole world, a flat projection breaks down, and the distance near the poles gets wrong. And that's why we need to have a geography data type here. And in point 4 release, we rewrote the geography type on top of S2 geography. And that's a library written by our Sedona PMC member, Dewey Dunnington. That's a library that wraps Google S2 geometry. And you now get more than 30 functions that work directly on the sphere. Distance, d within, intersects, area, buffer, unit, and many more. And you can also do a range query like find all cities within 100 kilometers of Germany. And the distance is in meters and on the sphere. No projection, no distortion. And the spatial joins work on geography too, like STD within joins. And another one, so I mentioned this a couple times before, the GPU accelerated spatial joins. I plan to have Sedona committer Liang Geng join our office hour in the next few months to talk about the GPU accelerated spatial joins. Some context first. So spatial join is the most expensive operation in spatial analytics. So think about joining a billion points with millions of polygons. So on CPU, this can take hours, and the modern GPUs can do this work in parallel much faster. But you need to leverage ray tracing cores instead of the CUDA cores, which turns out the CUDA core turns out to be actually sometimes slower than CPU. So in our work, we use things called ray tracing cores. So point 4 release ships GPU accelerated spatial joins. And look at the picture. The build side and the probe side are idle batches in memory. The GPU library takes over the filter and refine steps of the join. And the result comes back and as arrow batches. So 2 points. One, this is off by default, and you can turn it on with one setting. And you don't need to do any SQL changes. It will the curve optimizer will use this spatial join automatically. And secondly, we also published a Docker image with GPU support built in. Of course, you need to run that on a GPU that has ray tracing cores. It covers, so that enables you to run, like you have to run that on a GPU that has ray tracing cores, like RTX and L4 GPU, NVIDIA GPU. Okay, let's move on. Next, Parquet. So Parquet is the probably one of the most important formats for analytics. In point 4 release, we added write support for GeoParquet 2.0, and that is a new version of the spec where geometry and geography are the native Parquet data types. And then now you can write geography columns as well. When SedonaDB writes a file, it also writes spatial statistics. So later reads can prune row groups that do not match your filter. You can also use sort by geometry to store data spatially before writing, and that makes the pruning much more effective. And on the read side, we also handle geo-arrow 1.0 and 1.1 and 2.0 encodings. So files from the other tools just work. And as I mentioned, 0.4 adds 26 new functions, which brings the total to 176. On the vector side, functions like strelate, strnormalize, also the casting between geometry and geography. On the raster side, a whole new family of raster functions. Rs from path open raster from URL or file path. Rs shape, Rs slice works on n-dimension arrays, and Rs contains, Rs intersect are spatial predicates between rasters and vectors. And the last 0.4 feature, and my favorite, n-dimensional arrays. Some context first. A lot of scientific data is not a flat image. So weather data has time, height, latitude, longitude, 4 dimensions. And the standard cloud format for this is ZAR. 0.4 ships a new extension called SedonaDB ZAR. You can register that, and then you can read the ZAR data cube like a table. And the keyword is lazy. You can ask for the dimension names, the shapes, the size, without actually fetching a single pixel. So I will stop here on purpose because our Sedona committer James gonna did lots of work on this, and he will go much deeper at the end of the session. So before I move on, a quick look at what is coming for 0.5 release and the 3 theme, the geography, right? We want to continue cover more functions that are available already on Postgres and BigQuery. So we want to cover more and more function for geography. And second, point cloud. And the readers in SedonaDB for point cloud data exist, and some basic functions also available. But we want to expose them to Python and R users, not just SQL. And third, keep building the raster and ND array foundation with more formats and more functions. And also huge thank you to all 15 contributors of 0.4 release, and especially our Sedona PMT member Dewey Darrington, who drives the development of this awesome project. Cool. Another quick sneak peek of upcoming Sedona 191 release for Sedona Spark, Sedona Flink, and Sedona Snow as well. So these functions are the following functions that are they are already available on the master branch. So basically, this is a preview of what's coming. First of all, geography tab as well, and with a full set of SQL functions, right? Secondly, a new lightweight box 2D type with fast Parquet pruning, and third, a 3D version box 3D for point clouds and volumes. Fourth, and more raster work. Let me show you some example. First of all, the geography tab. In SedonaDB 0.4 release, we added geography joins, and now the same idea comes to the distributed Spark engine with a full SQL surface. So a geometry works on flat plane, and a geometry works on sphere, right? So we added a full set of functions, and look at the pictures here. Predicate, ST intersect, ST within, ST contains, ST equals, ST within, and the measures including ST area, ST length, num geometries, and the constructors and output, ST buffer, ST centroid, so on and so forth. And also a broadcast join strategy for these geography predicates. And we also fixed some cracking specs that we had before. And the second, the new box 2D type. A box 2D is just a 2D bounding box, min x, min y, max x, max y. It is small and cheap, and it is very good for filtering. Look at the picture here. So imagine a GeoParquet file with several row groups. So each row group stores a bounding box of its data. So when you run this function called stBoxIntersect against an area of interest, so Sedona use this box statistic to skip row groups that do not overlap. And in the picture, only row group 2 is red, and the others are skipped. We added many functions, such as constructors, such as stBox2D and mixbox2D, and also helpers like stExpand, also predicates, stIntersect, stBoxContains, so on and so forth. And third, box3D. So this is the 3D version of box2D. It adds a z-axis. So now the box has min max for x, y, and z. And why do we need this? This is for three-dimensional data, right? For point cloud data and for like LiDAR data, building space height. So we added the same family of functions, but in 3D. Constructors such as box 3D, right? And also predicates such as 3D box intersect, 3D box contains, so on and so forth. And there are also accessors as well. And some raster improvement in Sedona 191. So on the left, some new capabilities. We now support distance joins for raster predicates. You use RSD within. We also have a new GeoTIFF metadata data source. It reads only the metadata very fast, and the stack reader in SedonaDB raster now understands cloud cover and snow cover fields, and this helps you filter satellite scenes before you load them. And on the right, quality and flexibilities. So we fix a number of bugs, and another very important thing for the raster is that we now actually fully support raster UDF. So basically, you are able to create a UDF on top of the raster data tab, and the raster data you read in the UDF, the raster data going to be loaded as a NumPy array. You can basically apply any data you want, apply any NumPy function you want on the raster data, and not only that, you can also load that into rasterio format. So the raster data type. So you can also apply raster functions on top of this inside this UDF, and the result can be serialized back to the raster data type inside of the Spark. So this is pretty much the preview of Sedona 191. It is coming soon in the coming like 1-2 weeks. So please stay tuned. All right, community, right? So as I mentioned before, so we recently released a book for Apache Sedona. So this is O'Reilly animal book. So if you're interested, you can go to O'Reilly website or Amazon. You can buy there, but you can also get a free copy for from Wearables. You can search on the internet and then you can get it. I can copy the link here. I can paste that in the chat. So if you're interested, you can download free book, download the free book from there. And as you know, Sedona is always calling for help. You don't have to contribute like critical code to the project, but you can participate in the documentation and also contribute notebook examples to Sedona. You can also participate in the release testing. So you can help us verify the signatures and also run correctness tests. And by the way, all the release testing only happens on our mailing list. So if you want to participate in the release testing, you need to join our mailing list and subscribe to the updates. And share a story, right? So if you use Sedona at work or in a project, you can tell us, and we can feature your success story and live stream like this, right? Or on LinkedIn in a separate one. But we always welcome uh, the community to share their story and talk about the features they love in Sedona. You can reach out to me through email. My email is there, and you can also find us on Sedona Discord. And there are many. I think the screenshot here is not correct. So there are almost 700 people on our Discord, and they're pretty active. So you can also join us there on our Discord and also find us there. Now, let's hand over to our guest presentation, James Willis, who is the new Apache Sedona committer, and he's going to talk about the n-dimensional array rasters he worked on in the SedonaDB point 4 release. So I'm gonna promote James to the panelist. And James, please feel free to share a screen and take over.
Yeah, give me 1 second to get set up here.
Yeah, looks good.
Awesome.
Great, great. Go ahead.
Okay. So, yeah, as Gia said, he gave you the overview. Recently, I've been working on n-dimensional raster support and ZAR and SedonaDB. Before this 040 release, we had the raster type and we had some very basic, I would call them metadata operators for rasters. You could get the width or the height of a raster. Um, and so raster data is increasingly a data cube. So in Sedona Spark, you can load data that I might summarize it as it looks like a TIFF. You have an X, you have a Y. It's probably georeferenced, and it has bands. So you can have your RGB or your different spectra, whatever. But increasingly, time climate data, satellite data is being served as a data cube, which means that it has more axes than X and Y, or like X and Y and the band. So as I just said, we took the 2D grid from Sedona and SedonaDB, and we made it such that it could support an arbitrary number of bands, or sorry, dimensions, which we'll call like a data cube. So before this, you had some options, but none of them really involved using Sedona directly. Either you could flatten the cube out into planes and stack all the other dimensions into bands, but then you lose their meeting and their adjacencies in the non-spatial dimensions. Or you have to leave the Sedona ecosystem and Sedona DB entirely for a piece of software like Xarray. And I have the illustration here, and one thing I really just want people to take away from this is that in the system we built here, X and Y are still spatial and they're treated as a little bit special here. But you can have arbitrary other dimensions like time or elevation, level, year, band. And the other half of this project, other than n-dimensionality, was ZAR. So ZAR is I would call it like a cloud native format for storing these data cubes. So it has solutions for reading and writing in an object store, chunking compression, arbitrary dimensionality, composition of the various dimensions that are defined in a ZAR store for different variables of different dimensionality. And increasingly, it is being adopted by large raster and data cube datasets, where previously you might have been working with like GRIB files or NetCDF. So the ERA5, the Sentinel satellite imagery archives, the HRRR, which is the premier weather model from the American like weather forecasting service, um, are all being served out of object storage in ZAR these days, and the GeoZar spec is heading towards standardization, which is a specification for how you define um, the spatial extent of a data cube. Because ZAR is a generic format, but GeoZar helps you understand where on the surface of the Earth is this ZAR based, how do we interpret the location of each pixel, and so on. So today you probably have to use X-ray to do this work. Um, it says here no SQL data frame engine treats a cloud cube as a first-class queryable table. I was thinking about this line in the minute before I came on, and I need to caveat this. Um, there's like SciDB and Rastaman. Those those don't prove this statement false. They don't implement SQL, so that's technically true. But I can't remember who's been working on an X-ray SQL engine that treats each pixel as its own individual row. But there's this project X-ray SQL, which has like another interesting like twist on providing a SQL interface. But it's a fairly distinct approach from what we did here, which is what I'll get into. So we added the raster type, or I shouldn't say we added the raster type. That's exactly the opposite of what I mean to say, is that we took the existing raster type and we extended it to n dimensionality. I didn't want to create two distinct ecosystems or types or need like type-based polymorphism in our raster operators or anything like complex like that. We just have a single raster type. It's completely backwards compatible with what we had before. But now you can just have an arbitrary number of bands. Um, we package it up. We package up the ZAR functionality in its own extension called Sedona ZAR. We brought in 8 new RS functions in this release, and we have a bunch more slated up on main or in pull requests today. And then we also have georeferencing across real world ZAR metadata, which can be like very complex. I don't have the exact count in front of me, but last time I was doing the permutations, there's at least like 7 different ways you can describe where a ZAR is on the surface of the Earth. And you'll actually and when I say that, I don't mean in the abstract. I mean that I've personally encountered in real life various permutations of bounding boxes and georeferences and what order the terms in the bounding box are, what order the terms in the georeferencing array are in, um, various field names. So we not all of them landed in 040, but we did manage to pin down what I think is all the like somewhat standardized ways to georeference a ZAR. So they should all like localize themselves correctly on the surface of the Earth. Um, Along with this, we didn't just build the Sedona ZAR extension, but we started to lay the basis for an extension system. This one Dewey helped me with a lot. Um, this is a way to, in Python, have functionalities that extend SedonaDB in a similar way that you can install extensions into Spark or Postgres. We also built a lazy and pluggable byte loading system. So, as Gia mentioned earlier, the rasters in our raster system, be they GeoTIFFs and traditional 2D rasters or data cubes, ZARs, whatever, however they're defined, the pixels are not loaded into the database until a function needs to access the actual pixels. So loading a ZAR or loading a folder of GeoTIFFs it doesn't do anything until you call something like zonal stats that actually needs the pixel values themselves to perform its operation. And so this means that, if we're doing operations that prune the spatial extent, we're only looking for the rasters in this B box. That means we never load the ones that are outside of the B box. It makes like pruning operations that much more effective. We also handle like when you need to load them with an optimizer rule that injects async loading automatically. So this means that UDF authors, like if you were going to come and contribute a UDF, you wouldn't have to worry about the like pluggable or sorry, the lazy loading stuff. It's like, let's say, automatically resolved for you. All you need to do is denote that your UDF will want to access the pixels when you define the function. So it's transparent to users and authors. And we also have a zero copy functionality to and from NumPy. Um, I need to caveat this one. I'm not sure if this landed before we cut the release. But if it's not out now, it'll be out at some point in the future. It's already on main. So this is the code for reading a ZAR data cube. This is so you start your context, you register the extension with it. Each of those is its own line. The starting the context is maybe something you're familiar with if you've used Sedona. Um, and then we basically pass in this new context.read functionality that Dewey built for us. And one thing to point out here is that we have this arrays option. So with ZAR, you can have many arrays or variables. They may or may not have different data types or permutations of dimensions. One thing that we enforce when loading arrays into bands, bands is the language that we use in our type, is that they have the same dimensionality and the same data type. So arrays allows you to select only the ones that are relevant to your specific use case. And one thing is that about this example is this doesn't need any pixels, so it doesn't load any pixels. So we'll call this like almost instantaneous. And one thing about a data cube is it's kind of putting aside storage considerations. It's like this, it's not continuous. It's obviously discrete, but it's one entity, right? One data cube. So how do you create a data frame out of it? Do you want to create one row with, a terabyte of data in it? I don't think that's like an ideal interface. And also there's prior art here. PostGIS, and Sedona both have raster systems. And those treat like, you have your one geotiff that becomes one row. So what were we going to do in the ZAR world? Well, ZAR is naturally already chunked up. This is part of its like cloud native nature. So let me go back so I have a visual reference. You can imagine the grid drawn here as like the chunks. So across X and Y, you have four steps, and across this time band that's drawn, you have three steps. And so each of these little chunks is like the smallest unit of pixels that you can retrieve from object storage. Um, so in the example here, it has a 4x4 spatial grid, and I believe it has 3 years of data, or it's 6 years of data. So that means that overall you have 96 chunks. That's how we arrive at 96 here. Um, each row is geo-referenced to its local spatial extent, right? They don't share the exact same spatial extent unless they share the exact X and Y extent locally to the origin of the raster. Um, and so the storage layout is reflected in the layout of the data frame. And here's like another few operations where you're not accessing data again. You're only accessing the metadata of the raster and its chunks. So on the left, we have the several functions that are metadata operations. These help you reason about your ZAR. These help you like construct your understanding of the data set you're working with. And then on the right, we have some of the operators that we implemented in 040 that do access bytes for now. So slice is like selecting a single row. Like imagine you have XYZ. You can select Z equals 1, and then the result is only an XY raster. It's two-dimensional. You have slice range, so you only want years 2 and 3 from something with years 0 through 5. Dim to band. This is to deal with one of the realities of how ZAR is stored. ZAR is very flexible. So you can have your bands can be one of the dimensions in the cube, or each band, and I think thinking of band in the traditional like TIFF sense, can be a separate kind of cube. So dim to band lets you go from one to the other, and band to dim the vice versa. So dim to band is like you have one cube, and you want that dimension, each step along it to become its own cube, and band goes in the reverse. So you can pull it into NumPy, you can chunk the grid on the map. There's just more examples. Sorry, it's cut off because I've made it larger to display. It also handles the ZAR meta zoo. I described this earlier, but there's primarily two standards for working with ZAR data, but not all these made it into the release. But in main, you don't have to worry about this. I think any ZAR you find that is georeferenced will correctly geolocate itself on a map if you plot it or show the envelope or whatever. Or if we had these functionalities, do like a spatial vector, raster vector join. So I think we can shorten this slide into simply like your ZAR should georeference itself correctly if it's georeferenced. If it doesn't, cut us an issue and I will fix it. Another interesting thing that we did before this release, we did not fully support WKT1 and WKT2 projections or coordinate reference systems. So both in the raster and in the vector world now, we can, you know, take in, preserve, and utilize your coordinate reference system as long as Proj can deal with it. So these are some numbers. Keep in mind that these are from my laptop with my crappy home internet, and I mean that genuinely that my home internet is quite bad. If you have a good internet connection, these numbers look better. So it takes about, for that same data cube that we've been looking at, it takes 4 seconds to do the count. Same for SRID, shape, or dims. Envelope, all these are metadata operations. They take basically the amount of time they take is the loading time. To show 5 of the chunks is about 10 seconds because then it has to pull in the data itself to show the chunk. And then to materialize all of the data, it takes 110 seconds. Um, so these metadata operations are basically constant time because they're just arithmetic on the top level JSON file of the ZAR. Um, and then talking about the internals a little bit, this is the schema. How am I doing on time, Gia? This is the schema. We have,
You got 10 minutes left.
oh, I have plenty of time. We have like the coordinate reference system. This is the same as your vector world. Your geotransform, this is the same thing from GDAL. This defines where the top left or bottom left, depending on the CRS, corner of the raster is and how you like step through the X and Y space. So then using this and using the geotransform, you can figure out where like whichever pixel is on the surface of the Earth. We have spatial dims and spatial shape here. These are important partially to provide backwards compatibility and partially because we treat the spatial element as distinctive here. So you need to know which of your dimensions are the ones that refer to its location on the surface of the Earth. And that's what these help us do. Um, and then we have our bands. These are like individual like variables, right? It might be R, G, and B might be your bands, or different wavelengths, or whatever it is you're mapping. And these can be like kind of independently defined. So we have metadata, but we also have where the data comes from. So the URI and the format. And these are important to our like lazy loading system. So this is what enables us to wait until the very last second to load the data. Um, and then, so if the data has there's a field called data here. If the data has pixels in it, we have the bytes and we don't have to load them. If they're not there, we will use the URI and the format. The format tells us which loader to use, and the URI tells the loader where to get it from. So in this example, we have an anchor on the URI that says array equals rain underscore OK and chunk equals 032. This tells it to which chunk to grab and what variable or what array to grab it from, so that each row is correctly loaded. And then the last thing I'll talk about on this slide is the view. This is a feature that we haven't completed yet, but this is something that I'm really excited about. This is basically going to allow you to do a lot of operations like the slice we talked about earlier without doing any memory allocations or any copies, or even without bringing the data into the database, by allowing you to just say, this is the bytes, and it's not, to describe n bytes, you don't need n bytes of descriptors. It tells you like which bytes to select in the um, data without actually like performing the operation to allocate a new vector that selects only those bytes. So the big takeaway here is like this is how we load bytes without doing it so eagerly. And also this is how we maintain support for 2D and properly handle the spatial extent of a raster. So we inject this ensure loaded UDF, and users can call this if they need to ensure that it's in DB for like some kind of serialization work, or if they're pulling in a NumPy or something. But generally, for working within SedonaDB, you don't need to call this. But this is the function that reads the pixels. So any UDF that is tagged with a piece of metadata called needs pixels gets rewritten so that it is wrapped in an ensure loaded functionality. We use an async scalar UDF from Data Fusion for this. This is important because it means that, um, so we're doing IO, right? We're reading out of the cloud. So and we're injecting this indiscriminately. Every single record could be in DB, and we would still inject it. We don't really carry a statistic that tells us that. So it needs to be pretty cheap in that path where it's a no-op. The data is already in DB. And it also should be async because you're doing something that's best suited to an async workload, IO over the network. Luckily, we get this async IDO or async IO, async UDF, which we're using for IO. And these mean that, how do I describe this without getting into the internals of data fusion too much? Basically, they become like they get executed inside the parent expression scope. And so if there's no extra layers of a traditional UDF is bashed into these large groups. That's totally unnecessary for this operation because it is not bounded by the compute or the ability of you to move stuff around into registers and RAM. Um, and so it basically gets processed like per row inside the calling scope. And this means that whenever the data returns, you could start working on the calling scope. It winds up being more efficient for these IO bounded operations. It also means that if you're gonna like immediately discard the bytes, you're not holding a vector of like 8,000 records with all of the bytes of all of those raster chunks loaded. It also has volatility stable. I mean, this is just descriptive of what it is, but it was also like very important because it means that we get common subquery elimination. So if you are calling the same raster several times, and then it gets in a single project operator to slice out, year one and year two and year three, and you're doing, change in NDVI over multiple years. Common subquery elimination means that you don't load the raster three times because you describe it three times in the project operator. So kind of like a simple thing, but it was like very critical to avoid repeated IO of like these what can be very, very large and expensive rasters. And then SD restore metadata reattaches the raster extension metadata that the async UDF boundary strips. If anyone's thinking about going and using uh, async scalar UDFs in Data Fusion, I would just warn you that there are definitely some bugs in it. Specifically, it strips metadata out of extension types. I think maybe most people don't have to work with extension types. And then the other one is you can't stack them together if you inadvertently wind up with async UDFs, calling async UDFs, the whole thing just fails at evaluation time. But the former we solved for ourselves and our types in Sedona, maybe only for rasters, I don't remember. And the latter is still at large, so be careful if you're coming in here and building async UDFs in SedonaDB or another data fusion database. Czar is a plugin. We talked about this a little bit. I'm gonna kind of skip through this because I don't understand how this works. Dewey had to do this for me, but he wrote a bunch of code that I barely understood. Um, but one thing we wanted to make sure is that like a through line through this is like zero copy because rasters could be so large that like the memory allocation can both cause you to crash, but it can also just nuke your performance even if you don't run out of memory or something. And then what's next? So what we're working on now is a full raster analysis toolkit that is natively ND. We're working on point sampling, clip, polygonize, rasterize, geotiff exporting, tiling, resampling, kind of the classic RS operators from Sedona. Sedona Spark, but to the extent that they make sense with ND support. Vector raster joins. Uh, Once again, this is a feature we already have in Sedona, but we want to bring it to SedonaDB and the data cube. Um, Lazy views. I talked a little bit about this earlier, but this makes it just so that some operations don't pull IO. And even, I don't know how we're going to do this one, but we hope to even do lazy view pushing, so the loader itself can evaluate the view and immediately discard the unnecessary bytes by the time you actually have to do the IO. Um, Smarter scans. So right now, when we're loading the ZAR, we don't get good threading on the scan. This is a smaller kind of bug fix. It's not a bug fix per se. We knew what we were doing when we implemented it, but just getting more parallelization for ZARs with large chunks. And we're also exploring some new ways to work with raster data in SedonaDB. We know that SQL is not always the most ergonomic or intuitive way. We know that making the chunks opaque to the user is maybe not necessary in a sufficiently smart system. So we're looking to see what we can do on this front. So go ahead, try it yourself. There's a tutorial on the website. There's a blog post as well. Um, and there's plenty of public data cubes. My favorite one is probably the HRRR weather forecasts. All right.
James, there is a question in the chat.
Okay. Help me. Oh, let's see. Aggregation on a dimension in the cube over an arbitrary area. Okay, so an aggregation on it. Would this be, are you saying you want to aggregate across the non-spatial dimensions? Or you want to aggregate across spatial dimensions or arbitrary dimensions? I don't know how to get clarification on this question given our setup here. Spatial dimensions. Okay, so we are working on zonal statistics. That's like that'll be an RS function, and so in the data cube, what this will mean is you can run spatial statistics, and it'll run for each like plane, each spatial plane or each spatial slice. Um, so if like Z is your third dimension, you would get zonal stats for each Z value. You get an array of them where the index, it's their parallel arrays to the input. Well, you know what I mean. Yeah,
All right, great, James. I think that's all the questions from the audience.
awesome.
Uh, yeah. All right. Yeah. So I think time's up, and thank you everyone for attending the community office hours this month. And we are looking forward to seeing you next month. Thank you all.
Bye
Bye.
all.